Okay, so thank you for the introduction and thank you for inviting me for the seminar. I'm very happy to be here. And so, as you said, I will be speaking about some of my recent PhD work, which focuses on this dynamical low-rank approximations for Kalman filtering. And I think we'll jump right in. Just before this, I would like to acknowledge the two people with whom I've collaborated on these projects. So there is, of course, my PhD advisor, Fabio Nobile at EPFL, and also Sébastien Riffaut, who is also currently at EPFL. So the plan for today is, in a sense, quite simple. I'll just begin by making a small overview of the core tenets of data assimilation and make a small recap on what dynamical low-rank approximations are and how they're used. And then we'll try to bundle everything together and look at how we can derive some kind of DLR for filtering systems. And the story here is a rather common one in the sense that we're going to split it in two chapters. One, which is the theoretical case where we study linear systems, where in a sense everything is easy and reasonable, and we can make some very strong claims and understand deeply the systems that we're looking at. And then we move on to the more practical side, so real world applications, where you, of course, have nonlinear systems, and where essentially much of the theoretical guarantees that you have, they fly out of the window. But this somehow does not impede those systems from behaving very often very well. And so this is why we do this and how we want to see if we can actually get something of this DLR-ENKF system that's in that setting. So let us start with the introduction. The first thing I want to do is make a small recap on data assimilation. And so the setting here is a time continuous one. We're going to assume that we have a signal here which evolves according to this STE. So you have these affine dynamics here, and you have here an additive noise term. And the idea is that you're going to observe the signal via this observation process here, ZT, which, as you can see, you apply this linear observation operator H to the signal, and also you noise it. And then just to make things a bit simpler for now, we are going to assume that the initial condition of the signal is actually Gaussian. Okay, and now what is data assimilation? The aim is to combine your knowledge of the data and the model to get a better estimate of what the current state of the system is. A bit more mathematically and specifically looking at the filtering problem, the aim is to characterize the filtering density, so the law of the signal given AZT, where AZT is the sigma algebra generated by the observation process. So in other words, it's essentially given the data, how does your signal behave? What is its probability density function? Now, before I leave this slide, there is two more things I would like to say, namely the fact that we are going to consider a fairly standard setting in data assimilation in which the signal belongs to some state space RD, which typically is going to be orders of magnitude larger than where the observation space, so ZT lives. So ZT lives in RK, and one typical example of this is, of course, when you look at weather systems, you are basically have a system which you simulate using a few millions or billions degrees of freedom. But basically, in practice, you observe it in only a few locations, say 10, 15, or 100, or a bit more. And so you have essentially this discrepancy between the state space and the observation space. This will become relevant several times in the following slides. So that's the setting. And so the reason why I am looking at this fairly easy system of affine dynamics and linear observations and Gaussian initial condition is that in this case, we can actually solve the filtering problem exactly. We know that the filtering density that you get is Gaussian, and this means that, as usual, you can get away by characterizing its mean, MT, and its covariance, P of T. And so because these equations will pop up several times in the following slides, I think it's good to just spend a while to dissect them. So you have here the equation for the mean, where you see how you basically replicate the dynamics that you have, so the affine part of the dynamics. And then the way that you take into account the observations is you kind of compare the observation to what you get by applying the observation operator to the mean states. You take this difference, you pass it on to the, you embed it into the state space by this H transpose. And then, very important, you left multiply by P of T, which is the covariance. So this is the mean equation, kind of simple. A bit more tricky is the fact that the covariance is governed by this Riccati equation. And there is two things that I can say that are important. So firstly, it is a bit remarkable that this Riccati equation does not depend on the observation process Z of t. So it is independent of the observations. That's number one. And second, Although this here is basically the exact solution to the filtering problem, solving the Riccati equation is typically quite complex because, as I said, we are assuming that we have a large state space. So we have to assume that D is very high, and this means that this becomes a, I don't know, billion times billion matrix differential equation. Solving it is quite complex, and so people often do not do this. Now, this being said, this would be basically approach number one to simulate, to solve this filtering problem efficiently. I mean, to solve this filtering problem would be to simply simulate the mean and the covariance, which we often do not do because, as I said, this P of t can be very expensive to solve. There is another approach, which will be more closer to what we'll be doing in this talk, which is to kind of cheat a bit and seek essentially some kind of auxiliary process x of t, whose law conditional on the data is basically equal to the filtering density. And then the rationale is if you can simulate such a system, then basically you just get the filtering density for free because they agree. And it turns out that that is not too difficult to find. There is actually a whole bunch of processes who verify that their laws agree. One of the perhaps most famous example is going to be this vanilla Kalman-Bucy process, or in the rest of the talk, I will often be using the initialism KBP. And again, because this equation will pop up quite a few times in the following slides, I'll just take a second here to dissect it. Again, you kind of replicate the whole dynamics of the system. So you have here the affine term, the noise term. And again, you kind of integrate the observation by comparing the observation to what you get by essentially applying the observation operator with noise to your current signal. Again, you embed it into the state space. And again, very important, you left multiply it by the covariance. And so here below, I write that this system here is almost adapted for simulation-based filtering. And I say almost because currently, so this is a Makin-Vlasov equation. Technically, it depends on P of t, which is the covariance. And at this stage, solving this becomes basically as expensive as solving the Riccati equation here, which, as we just said, is very expensive and hence not very practical for large dimensional systems. But there is another approximation that we can make to make the system viable. And it is, of course, to take a particle approximation of this covariance, so a sample covariance. And then we naturally get one of the core objects of this presentation, the Ensemble Kalman filters. So the idea is you discretize your mean field equations into a set of particles. There is P goes from 1 to n. You have to basically create a unique pair of Brownian motions, both for the model and the observation space, W hat and V hat. Then you can define your statistics in the usual fashion. So you have here the sample mean, which is this, and the sample covariance, which is given by that. And then finally, you get the vanilla Ensemble Kalman filter, or ENKF, or VNKF, which is as such. And again, if you compare this equation here to the one from the previous slide, the main difference is that now everything is a particle version. And so in particular here, you have P hat T, so the sample covariance, which by now is a quantity that you can very naturally compute in this particle-based system. Okay, so this here is a setting and one of the very powerful tools that are used in current data assimilation, or rather basically is used as the basis for many data assimilation techniques. There is a few things I can say about the system. I'll start with the negative aspects. The first is that, as I said, this here acts as a basis for simulation systems, and very often people actually combine this with many other tools. I'll just mention here variation, inflation, as well as localization. But there is a whole wealth of techniques where people try to basically stabilize because these systems, because they tend to be a bit numerically unstable. And the other thing I would like to say, and this sounds kind of obvious at the moment, but I will get back to this, is the cost of simulating n particles. It's basically scales like the product d times n, in the sense that I like to think of this in terms of matrices. Your state space is Rd, you have n particles, you kind of have to evolve a d by n matrix, and there is seemingly no way around this. Okay, let's keep this in the corner of our minds for a second. The other thing that I wanted to say is that on the positive flip side, these ENKF systems are really well behaved for high dimensional filtering problems. As I said, they are practical, so you can efficiently get something that works. They are very often more robust than particle systems in these high dimensional systems. And perhaps most crucially for this talk is the fact that they tend to display really decent behavior even when you use few particles. So for like large dimensional systems, including the weather, so you have this, again, a few million degrees of freedom system, you simulate it using 20 particles, and it kind of works. You kind of get a signal tracking behavior. And when you think of it, this is actually conducive to suspecting that there is a kind of low-rank structure that must lurk in these equations. Why? If you again look at the shape of the equation, the only way that you integrate assimilation from the data is via this term here. And it's important to note that, as I said, you left multiply by the sample covariance. Now, if you're in a setting where you are simulating this with, say, 20 particles, and you have a system of dimensions 1 billion, you are basically correcting in at most 20 directions, because that is the rank of the sample covariance. And this means that somehow correcting in 20 directions is enough to basically be able to get some decent signal tracking going on and do some coherent data assimilation. And so this means that somehow there must be some kind of preferred directions along which you would want to assimilate, and you would like to be able, for example, to sample more particles along those directions in order to be able to be more precise in this in these preferred subspaces rather than like wasting your budget on many other particles elsewhere. And so this is how I get back to this point from before. Somewhat disappointingly, the ENKF in this formulation does not truly leverage this low-rank structure at a cost level. Essentially, the cost of simulating n particles does not intrinsically rely on this, let's say, intrinsic rank or intrinsic subspace that you would like to exploit. And so this is exactly what we propose to do in this work. And in this context, we're going to use a tool called Dynamical Low-Rank Approximations. So there is by now actually quite a few ways to introduce DLR, as I will be calling it in its short name. It has a varied history of stemming from quantum chemical physics, has also been used and rediscovered and analyzed in the matricial ODE context, as well as in the random field context. Given that this is a UQ seminar, I will stick to this random field approach as it is fairly meaningful, as we will see in just a bit. So the idea is the following. Imagine that you have a random field which is time dependent, which you can decompose in its Cahunen-Leuven decomposition. And so for the rest of this talk, these UIs I will be calling physical modes. The sigma i's times yi here I will be calling stochastic modes. And the idea is that the physical modes only have dimension, each of those has dimension d, whereas the stochastic modes, at least once you discretize them, they're going to have dimensions n. And the idea is a fairly simple observation. If the weights sigma I go to 0 quickly, then a good approximation of your original random field is simply given by the truncation to the rth term. So you basically only need to characterize the mean, and those are physical modes, and those are stochastic modes. And then again, here the gains become quite evident. Rather than storing a d times n system, you would only have to store d times r particles and d times and r times n, d times r physical modes and r times n stochastic particles. And of course, if r is small, you can have some very interesting gains. This, of course, only works if you know how to basically propagate the ui's and the yi's. So if you have some closed evolution equations to characterize how these modes evolve. And again, there is by now a wealth of literature on this topic. If we look at SDEs, the most close approach we have is some work by some colleagues of ours, so Kazashi, Nobile, and Zokolan, in this paper here, where they basically analyze a set of equations that give you good evolution equations. So what DLR looks for SDEs. And so you have an idea of how to evolve the systems in this setting here of SDEs with only two terms here, which does not correspond to our filtering setting because we have an additional term. And so now we want to basically, at this point, combine this idea of DLR and integrate it into this filtering setting to be able to get some computational speedups and see what we can get along the way. So this was the introduction. Now we're going to begin to see on how we can actually define this DLR for data assimilation setting. And as I said, there are basically two goals in this section. The first is to derive a principled DLR reduction for Kalman-Bucy processes, which is essentially this mean field object that is very well understood. And then as a second part, which is kind of the ultimate goal of this section, is to find a good way to extend it to a particle-based filtering setting, because that is what people use in practice, and that is, of course, the interest of this whole work. But as I said, we want to do this in a principled way, and therefore we have to start at the very root and say, okay, if we are given a general process like this one here, so we have this term, the drift diffusion, and also this extra term here, which is the additional Ito process. So in our case, it's going to be the observation process. How do you come up with a suitable DLR formulation for this? So like a good way to evolve both the physical and the stochastic modes. And so just to give you an intuition on how we actually come up with those equations, it's basically a matter of establishing a wish list, if you will, of properties you want your system to verify, and then try to use them to derive a set of corresponding equations. So to give you the idea, we want our XDLR here to be an approximation of the true process. We want it to have this low rank decomposition for a fixed R for now. So here again the mean, and here again the physical modes, and here again the stochastic modes, which I will often write as such. And then we want basically both the mean and the physical modes should obey differential equations of this type here, where you have these coefficients alpha and beta, which you need to characterize. And you can see they do not depend here on the Brownian motion term. This here should only be taken care of by the stochastic modes. So this is how you make the separation between the physical and the stochastic modes. It is the stochastic mode's responsibility to take care to absorb basically the Brownian motion term. And then the last constraint that we impose is something that is fairly common in this DLR world, also called the dynamically orthogonal method in the words of Lamieux and co-authors, which is basically here just a constraint that you add on the dynamics to reduce the redundancy that appears in the equations. Now, this here is the basic recipe that we have. We do some extra work, and then we get the following mean-separated DLR equations, which you can see here on this slide. Now, I apologize. This is, I think, the worst slide I will show during this talk. And I just want to briefly walk through the equations and show you how they make sense at an intuitive level. And then I will explain how we actually derive them in the first place. So you can see there is actually like a bunch of fairly natural elements that jump, that arise when we look at the system. Here, for the conditional mean of this process, you can see that basically it corresponds to filtering out the mean by taking, in essence, conditional expectations with respect to the sigma algebra AZT. It's actually a little bit more tricky than this, but intuitively it works quite well. Then you have here the equation for the physical modes, which is the perhaps most ugly one. And so for people who are more familiar with the DLR aspect, I will just mention there is this extra term here, g of t, which has a fairly nasty expansion, which is basically a correction term which arises from the fact that both u and y are at this point non-differentiable processes. And this is somewhat different from usual DLR formulations and something we had to work on establishing. And then finally, perhaps the most intuitive equation that you have is the one for the stochastic modes. You can see how basically it corresponds to taking the dynamics we had on the previous slide and simply projecting them onto the range of u of t. So it has a fairly nice intuitive explanation. Now, the way that we actually come up with those equations, beyond the fact that they verify all of the requirements I listed in the previous slide, is this following theorem, which kind of guarantees that essentially if your true process has this form here under a bunch of other technical assumptions, then you can guarantee that the triplets associated to the true process would solve the DLR equations. And so this is the rationale of saying, if you are exactly low rank, then you verify those equations. And then the question is, if you are near low rank, do you think that these equations will be a good approximation of the near low rank process? And so that is exactly what we will uncover in the following slides. And I quite like the punchline. Basically, yeah, if x true were exactly low rank, then it would satisfy the DLR equations. But now we basically take these DLR equations, we can apply them to any system and see, do we get a good approximation? So this here is the general setup that we have, and now we want to apply it to the specific case of Kalman-Bucy processes. And so that is the next step, which, as you can see, simplifies the equations a fair bit. So now we are going to have this x DLR KBP process, as I will be calling it from now on. Again, we have an equation for the mean, the physical modes, and the stochastic modes. And there is already a few things that stand out from this from the system. You can see here how the equation for the mean is basically the exact same one that we had before for the Kalman-Bucy mean. So it is quite nice that without doing any work, we naturally recover the mean equation of the Kalman-Bucy process. The equation for the physical modes here, it simplifies substantially. Basically, you can see here that you don't have this dzt term anymore, and this means that u of t becomes a differentiable process. And this actually gives you an even extra added benefit. Namely, if you impose U0 to belong to the Stiefel manifold that you see here, then you can ensure that UT is going to remain in the Stiefel manifold at all times. And so this is quite convenient for several reasons. So which I will get to in the following slides. And again, in a sense, most intuitive equation is the one for the stochastic modes, where now it's very clear how you basically just project the dynamics onto the range of U of t, and so have these equations in reduced dimension. Now, there is one more thing that I would like to say. It's, as I said before, you don't see a z of t appearing here. You don't see a z of t appearing here neither. And this is maybe a bit surprising after having spent all this time setting up the system as such. But when you think of it, previously in the Riccati equation, we didn't see the z of t, so the observation term either. And so since the ui and the yi's are responsible for tracking the deviations from the mean, and basically like they take care of the covariance, then not surprising that neither here does the z of t term appear. Okay, so this is the first observation, but we can also go a bit further. What else can we say about this DLR-KBP system? And so it turns out actually quite a few things. The first thing is, and I'm going to use this notation here of just calling it XT instead of XDLR-KBP because it gets lengthy to say and to write. But the idea is if you reassemble the object and look how it behaves in the ambient space, so in the state space, basically the XDLR-KBP process verifies this equation here. And the crucial observation is that under these conditions, you can show that this is actually also an inhomogeneous Ornstein-Uhlenbeck process, which means that it is Gaussian. And this means that, again, just like before, for the KBP, you can get away by characterizing its mean and its covariance, which we did. So we have the same equation for the mean as we have already discussed before, so I won't come back to this. And we also have the following equation here for the covariance, which, if you look at the first three term, behaves exactly like the Riccati equation. You only have this last term here, where you basically project the sigma term, both left and right, onto the range of P of t. And this is essentially what guarantees that you remain low rank. And basically, this is also the main difference between the Kalman-Bucy process and the DLR-KBP. Basically, this term, so this deviation here. We can actually even go one step further because we know that the covariance has a low-rank structure. And so this means that if we define here this reduced covariance, which has dimension r by r, rather than solving the previous equation on the slide, which was still a d by d, we can get away by simply solving this evolution equation for the physical mode, so d times r, and then here this reduced Riccati equation here, which is an r by r. So you can get some very interesting computational gains by doing this. And so this here I would kind of call algorithm one. If you want to solve such a system efficiently using a low-rank approximation, I would do it using these equations. Now, there is two things I want to say here. The first is the fact that we are quite happy when we derive those, and then we subsequently realize that we are not the first ones to propose the equation. So some other people, and so I link here the work of these colleagues, have basically already proposed these equations in a separate fashion. But the difference is that basically through our approach, we show that these equations here are not only low-rank approximations of the moment of the given systems, they are actually the exact moments of an underlying low-rank approximation process. So we kind of push back this analysis layer one step deeper, and this allows us to make some very interesting observations and claims about the corresponding system. The other thing that I would like to also say on this slide is that so there is actually many people who work on these modal type of reduction for assimilation systems, and one other very clear connection we saw is some work by these other colleagues here, where basically they apply DLR techniques for filtering systems, but with a time discrete observation setting. So they had to solve a Lyapunov equation rather than a Riccati one. And they basically, in the time integration scheme they used, they also encountered an equation which looks similar to like a projected reduced version of the system. So there was overlaps with many other works in the literature, which was quite interesting to also find out as we worked on this. Okay, so now that we know this, another question is, how does this equation for the physical modes behave? And so again, we did some proof and we did some work and we were quite happy. And then we realized that this was actually already well known in some other areas. So specifically, this equation here is actually called an OJA flow in the machine learning community. And so there is one obvious thing that you can say is that in general, you don't have any convergence guarantees, right? You simply have to take A to be skew symmetric, and then this system keeps spinning on forever and ever. But it is kind of known, and so we looked at a slight generalization of this, that if A is symmetric, then you can guarantee that U asymptotically aligns with the R most energetic modes of A. Um, so basically, this kind of like acts as a detector which converges to the dominant eigenspace of A, I mean, to the R dominant eigenmodes of A. And this was also interesting to realize because then we also saw that there was a connection to another branch of data assimilation and reduced models, which is called this assimilation in the unstable subspace, where basically people use only assimilation in the unstable modes of the system in order to guarantee stable convergence, so stable filtering. And our system essentially asymptotically recovers exactly this behavior. So this was also an interesting connection to make. Okay. So now, as we have all these properties that are lined out of the system, we get to the part where I want to briefly discuss when it makes sense to actually use this DLR reduction. And so it's important to keep in mind, we are specifically targeting the regime where the filtering density of a true given system has a tendency to concentrate on a low dimensional subspace, because else, of course, it doesn't make sense to apply a dynamical low-rank approximation technique. And basically, this is something that, as we said, has a tendency to happen, but does not always happen. So this is something that we need to know about the system somehow a priori. And basically, the best avatar of this situation would be if the filtering density keeps on collapsing and becomes essentially lower and lower dimensional, all the way to collapsing to a point. Imagine that you have enough data to fully identify the system, and you use this to have a perfect knowledge of the system. So this is like kind of the ideal situation. From a more mathematical point of view, we can actually characterize how the DLR KBP diverges from the KBP over time. And the key ingredient to this is to note that if you compare the KBP to the DLR KBP, the equations differ here by this factor there. And so everything here boils down to the size of this orthogonal defect. So we quantify it, but we cannot say a priori how big or small it's going to be. This is going to be system dependent. And just to spend one more second on this slide, I just want to outline a few situations where you can expect to have some very good approximation properties and where not. So one example where you do not expect to have this good approximation property is if you have a moderate or a large isotropic model noise. So if sigma is some small sigma times the identity, then of course, essentially, I like to think of this as you take your filtering density and you thicken it around the plane where you are. And so there is, of course, no low rank structure here at the level of this noise. That being said, on the other side of the spectrum, now there is actually quite a few situations where you do have this nice low rank density which appears. Typically, when you look at small zero noise, or also called perfect models, and which typically express a high confidence that you have in the dynamics. So typically you have this idealized test regimes, or when you have, for example, some very short resynchronization times where people know what's happening and they really know what the dynamics are in this given system, and they don't need to like solve for some unresolved scales or some such. Another situation which arises fairly frequently is the case when when the noise is itself low rank and structured. One example here is when you have this noise which enters through a low dimensional forcing map. So you have like these slam problems. And yeah, so like this is also an occurrence. And finally, one last situation is when the model and the noise, they share the same spectrum. So one typical example here is when you have these SPDEs, it's often studied, where the forward operator and the noise have the same spectrum. And then by the OJA flow slide from before, we know that the physical modes, they align with the dominant eigenmodes of the forward model, which if it coincides with the model noise is basically enough to guarantee that you can capture the most important aspects of the noise. So as said, there are situations where it is really advantageous to apply this technique and others where it is not. This is something that needs to be established a priori. Just to stay one more second on this topic, we also have a Granol type bound where we basically quantify. So depending here on this orthogonal defect, we can do a mean and covariance bound. And so by comparing the mean from the DLR to the KBP and also the covariance, you can see that you have these typical Granol bounds, which depend on the initial residue, here both in the mean and the covariance, and also here on the worst case moment in time of this orthogonal defect. And the constant here is actually exponential in time because we took the most general bound, but there actually also exists stronger results. So typically, if you have more restrictive assumptions, such as dissipative dynamics, you can reduce this to actually just like a constant term, which is independent of time, which is bounded, sorry. Yeah, so basically, we have also like this result, which quantifies how far we go in the worst case scenario. Okay, I think it's time for some numerics. I'll just look at a fairly toyish model where basically we have, again, like this typical setting here, where we then kind of get A and F from some upwind finite differences. Just to make things easy, we're going to observe the system everywhere, so full observations. And basically, we want to see how DLR behaves in the system. So the first thing I want to do is to kind of test this thing that I said before about the size of the model noise, if it's isotropic, how bad things can get. And so what we do is we take an experiment, we fix the rank, and we play with this model noise error. And you can see here, as predicted by the theory, as you increase the size of the isotropic model noise, your approximation, so the error between the DLR and the KBP, so the true one, gets worse and worse. And you have this behavior both at the level of the mean as well as the level of the covariance. This is not surprising, and again ascertains that the regime where like this makes sense is going to be when you have small noise, at least in these kinds of linear Gaussian models. This is you have to look at these small noise models for this regime. We can flip the script. So now what we do is we fix the noise model for something small where we know that you have some good approximation property, and we can investigate how varying the rank affects the quality of the approximation, because you also need to find the correct rank in this whole system. And so the idea here is, again, not surprising. Basically, if you have a very small rank, you can see here how the error shoots up. But as you take a bigger and bigger rank, the error gets smaller and smaller. And so you have, again, the same story both for the mean as well as for the covariance. And so finally, one more thing that you can do is you can actually say, okay, so far we've compared how well the DLR KBP approximates the KBP. But you can also ask, how well does the DLR KBP approximate the true signal? Because that is actually the relevant question. And so here, what you can see here on the left is we compute this, we take this RMSE notion to compare the DLR KBP mean and covariance to the true one. And you can see here that actually fairly quickly, so because there is a much larger error, you very quickly get to the same level of observation quality as the full auto model, so as the KBP does. And here on the right pane, I'm just doing a brief experiment where x-axis is the computational time and y is the RMSE. So this here is more expensive. So the FOM is again the full KBP model. And you can see here, as you take bigger and bigger ranks, it takes more and more time to compute. But basically, the IRMSE remains roughly on the same level, so you can essentially speed up those computations. This is, again, a really toy model, so you can expect a lot of more gains by having more serious systems, of course. Okay. We have now finished the first subpart of this first chapter, and now we get on to the actual meat and bones of this talk, which is to try to find an ENKF extension of the system, which is, of course, what people use in practice. And so again, our core object is going to be here, this interacting particle formulation, and we want to develop a low-rank analog. And so for this, the idea is kind of fairly simple, albeit a bit technical. You simply take your mean field DLR KBP process, you take these stochastic modes here, and you replace them by some kind of particle system type, so which are going to live in a reduced space. So these goes now from being essentially R stochastic modes to being R stochastic modes with P particles, and so each particle has dimension R, if you will. Again, what we do is to be consistent with what we did before. We want those stochastic modes now to have zero sample mean, and we simply redefine the new process as x hat, which now has u hat 0 is the sample mean, and y hat t, which is the stochastic modes, and p hat t is now the sample covariance. At this point, basically, you need to look a bit at the system and decide how you want to discretize it. And we took the following approach here for the DLR-ENKF. I won't spend too much time on these equations because they have a form that is by now similar and known to what we have seen before. Perhaps the only peculiarity is, as you can see here, we had to add basically the averaged Brownian increments for both the state model and also the observation model, because we wanted to ensure that these are consistent through the equations. Sorry, we wanted to ensure that the U hat really captures the statistical sample mean and that these here are zero statistical sample mean. And basically, again, the story boils down to when you do this and you reassemble things in the ambient space, you can verify that the low-rank particles verify this equation here, again, with the key difference being here this projection onto the range of U of t. So this system is quite nice, and it has, and we did quite some analysis. I'm going to go a bit quicker on this part. We established well-posedness of the system, and perhaps more importantly, or as a next step, once this is done, is we want to basically verify how the system behaves in the mean field limits. And so this is typically accomplished using these propagation of chaos type results. And so in the case of the ENKF, it is known by some work of Del Moral and co-authors that as you increase the number of particles under some technical condition of the number of particles, which scales like a product of the dimension of the system, so the state space, you can show that the individual ENKF particles behave more and more like their mean field equivalents. So there is this correspondence here, and you even have like a Monte Carlo type decay rate for this. And this bound here is uniform in the uniform in time, and it's this moment bound. And basically, we managed to recover the exact same results in our framework with the neat thing, which we weren't even looking for, but it kind of popped out naturally, is the fact that the condition that we impose on the number of particles scales like some product of the intrinsic dimension, so the rank of the given system, and then we managed to recover exactly the same results. So I'll just say at this point here that we are actually imposing a few more conditions. This works under the assumption of some dissipative dynamics and full observations, which are both necessary in this situation. But this is an encouraging step to say that our DLR-ENKF formulation is consistent and behaves in a good fashion with respect to the vanilla Kalman-Bucy process. Okay. I want to show you one more numerical example before we move on to the second part of this talk. So here we looked at a slightly more complex PDE, so an NSPDE, 2D, which is this following advection diffusion system with a stochastic forcing term. We consider two situations, full observations or partial observations. And basically, what I want to show you is this plot here. So left is full observations, right is partial observations, and I'm going to focus on the right one because things are a bit more clearer. And so we basically compare three models. You have the FOM p equals 10, so like the blue one, which is a small ENKF model with only 10 particles. And then you have the green one, which is the ENKF with 425 particles, so many more, and where you expect to see more of a mean field behavior already kicking in. And so what the shaded regions are is actually the standard deviation around the RMSE as you repeat the filtering experiment on multiple runs. And so now, between these two models, what we do is we wedge in a DLR model, so DLR-ENKF, with a rank of 10. So it has the same rank as the small ENKF model, but it has the same number of particles as the large ENKF model. And you can see actually already here from the slide here, you can see how basically when you have fewer particles, you have more variance in how the system behaves because it is more reliant on the individual behavior of each of the particles. And so you have a bigger variance, which is an undesirable feature. As you increase the number of particles, the variance becomes smaller because you are more in a mean field regime. And so you can see here, where is the DLR line? Well, you cannot actually see it. It is pretty much underneath the green line. And so this means that despite the fact that your system, your DLR, only has a rank 10, so like the small one, it displays the same stability properties and like the same increased variance robustness as the 425 model, which essentially was not guaranteed a priori and is very nice to see in practice. So like you really manage to basically get the benefits of having more particles while using a reduced rank to evolve your system. So this is very encouraging in this direction. Okay. So now we get to the last part of this talk, which is going to be about extending the system here to parameter estimation, which we use as basically like a good excuse to explore all of the issues that arise when you try to look at DLR in these nonlinear contexts. So just to make a small recap on what these systems are. Basically, we're going to assume that now we have a slightly different dynamical system. So we have this x true, which is driven by some deterministic dynamics, which depend possibly non-linearly on the current state, and also some unknown true parameter theta true. Just for simplicity, we're going to assume that we still observe everything with this linear observation operator h, noisy, but you can see here very importantly that we do not observe the parameters, right? These are unknowns. So now the name of the game becomes to not only estimate what the filtering density of the process is, but also to get a better estimate of what the filtering density of the parameter is. Ideally, what you would want is essentially this thing to converge to the true parameter, but basically this depends on the given problem at hand. And so here there is a technique that is fairly commonly used, which basically is called this augmented state approach. And the idea is very simple. You simply create an augmented state here as such, which has dimension d plus n theta, and then you create some fake dynamics. So you just augment the state, and here you have dx bar, which is just the dynamics, and here's 0. And then you simply apply the Ensemble Kalman filter equations to this augmented state system, and this gives you these equations here. And this basically induces a dynamic on the parameters. And despite having no guarantees in practice in this filtering context, this often has a tendency to converge to the correct parameters, to do some effective parameter identification, which is why people actually use these systems fairly often in practice, because they are so good at doing the job of identifying the parameter. And so we wanted to look at these systems and see what can we say, and can we use DLR to again accelerate these systems. And by doing so, we kind of naturally encounter quite a few issues that we have to resolve in order to be able to get something practical. And there is three main points which we address in our recent work here with Nobile and Riffaut. So first, we needed to extend our theory from before to the nonlinear case, which we hadn't done in this previous work. We also want to find a suitable time integration scheme, which essentially leverages all of the goodness that we know from both the DLR world as well as the filtering world. And then we also needed to look at a way to efficiently handle nonlinear terms, because if you have these nonlinear operators, it's unclear that you can make some serious computational efficiency gains if you have to evaluate the whole right-hand side at every single time. And so we kind of offered approaches to all of these issues, and I'm going to focus on the first two, because this one here is a bit more technical. But basically, the approach that we propose is somehow kind of simple with what we have like set up to now. And the idea is you can always start from the nonlinear equations. So that, for example, you know that you have a mean field nonlinear filter that somehow works and has some wet properties. You simply apply the DLR equations that we derived a few slides above, and then you use this as a basis to define a corresponding particle filter system. And this to us is the quote unquote correct pipeline to get some nice properties out of the system. And the thing that I should say here is that at this point, there is a whole variety of choices that you have to make. And here on the left, what I'm showing you is this nonlinear vanilla Kalman-Bucy process. You can see here the equations look fairly similar to what we have seen before, except that now you have this term here, where you have this f, which is nonlinear and depends on theta t. Here, the equation for the physical modes becomes a bit more ugly, but it's roughly the same idea. And then you can use this and our previous knowledge to basically define a particle filter version, which is consistent with its mean field limit or supposed mean field limit. We don't know it as such, but we have strong suspicions. The issue is that there is not only one Kalman-Bucy process. As I said, there are many other potential choices. So just to basically benchmark our method and see how it applies in other contexts, we also looked at a few other variants. So there is, among others, this deterministic KBP, which, just to cut a long story short, is you do not use this extra noise term here, and you make a few modifications to the dynamic. And this variant here is quite often liked in practice because it tends to behave a bit more stable with respect to stochastic fluctuations. And again, you can just take this, derive the DLR equations, derive a DLR-ENKF version of that. And so in our experiments, we looked at three different versions. So there is this vanilla one, which I described, the deterministic, and yet another one, which we call sequential, where you just remove another observation term, sorry, another noise term, which has its own benefits, which I won't get into in this slide here. And so One more thing that I would like to say is that at the end, what you can do is look at the time integration schemes, and we wanted something which combines both the efficiencies of the DLR time integration schemes. And so for this, we use something called the bug integrator, basis update and Galerkin. So this is the work of Teruti and co-authors, which you can find here. And basically, to cut a long story short, what you do here is you kind of try to first update both of the bases to get a good idea of what the next step looks like. And then you project your equation on this augmented basis to get essentially the next state. And somewhat importantly here, you do this truncation step because you have augmented the basis, you are of rank 2R. And so you want to truncate back to a current rank R to avoid that the rank explodes in time. And then basically we managed to put all of this in a forecast analysis type loop. And this means that actually we can do the analysis step purely in the subspace, which is also quite a nice feature of this, of course, if you have these linear observations here. And this here results in, at least empirically, a rather robust assimilation scheme, at least much more robust than other things that we tried. And so we're quite happy with this. And one more thing I would like to say on this slide is that it's fairly easy to actually build in a rank adaptivity. And so like this again ties in this idea I said before of you would want to be in a situation where you become more and more certain. And so like the rank collapses as you become more and more certain and you need a smaller and smaller space. And you can very easily do this here at this step rather than always truncating to a fixed rank. You decide how much am I willing to lose at each step and see what happens. Okay, now I just want to conclude this talk by showing you a few numerical experiments. So this one here is the first one that we did. So it's this Fisher-Kolmogorov-Petrovsky-Piskunov model. You can see here how you have this nonlinear reaction term and here a diffusion term, which depends on this diffusion coefficient, which essentially has this modal expansion on these psi i's that you see here. And you have this unknown parameter theta I. And the idea is we don't know what this theta I is. And what happens is you have an initial concentration, which starts here and kind of evolves according to the arc. And as it does so, it interacts with the diffusion coefficient. And the question is, if you observe this system, can you guess what the original coefficients theta I are? So we basically do exactly this. We apply this DLR-ENKF pipeline to these nonlinear systems. And then here on the left, I'm showing you the results of the parameter identification of the ENKF. And on the right, I am showing you those of the DLR-ENKF. And you can see here how basically you have to compare, so like the parameters one to one. Basically, the ENKF and the DLR-ENKF basically have this pretty much the same exact evolution of the parameters. So it manages to reconstruct the underlying approximation of the field well enough so that basically with a rank of 7, it's enough to capture the correct dynamics and ensure that you identify the system correctly. Just to show you here this result, some tables. This also tells an interesting story. So on the left, you have the full observation case. On the right, you have a partial observation case. And the idea is basically as you have full observations, there is less uncertainty in the system. And so it's easier for this rank collapse phenomenon to happen, if you will. And you can see here that basically with the rank, and so what I'm showing here is the relative errors. And you can see here, as you increase the rank, you very quickly get to the same level of relative errors as the ENKF. And on the other hand, when you look at partial observations, because there is more uncertainty, and so you expect there is a bigger intrinsic rank you need to track, you can see here how as you increase the rank, so you get better and better markedly between this rank R equals 7 model and the ENKF. And for the timings, the story is what you expect. A smaller rank equals a faster computation time, but they essentially all beat the ENKF at this stage. I'm just going to gloss over this slide. One thing to say that is important, and I will show it at the slide at the end, is that the thing that essentially was the most common issue in our simulations was there is a tendency to do covariance under approximation in the sense that it is easy if you have too small of a rank to be more certain in the uncertainty around your state than you should be, which happens by virtue of essentially you tracking fewer ranks and discarding some of the energy. And so that is a thing to be aware of. Just to conclude this idea of rank adaptivity, I just wanted to show that if you implement these rank adaptive mechanisms, you can see how, as predicted, you have like this very nice behavior of the rank adaptively says, actually, I need less information to be able to efficiently evolve my state. And as time goes on, it keeps bumping down and down, as in a sense you do a better and better job at like identifying the correct state of the system. And you also get some modest speed up in these examples, which was also interesting to verify. Just to conclude on basically the last experiment, which was a funny one. So this was a bit more involved, numerically speaking. So you have this human system of the arterial system. You have 55 arteries. And the equations, what you check is how the blood flows through the system, through the arteries, which you model using Navier-Stokes and some simplifying assumptions. And the idea is that you have to imagine that you have some trackers here, so in the neck, here in the arm, and here in the leg. And the question that you're asking yourself is, given essentially like this data, can you recover what the elastic coefficient, so this beta parameter here, is in the first and the 13th artery that you see here? And so we want to actually do estimation both of the state and the parameter. And so here the story is a bit more nuanced and shows the complexities of this. So you can see that for the first parameter, there is an excellent identification both for the ENKF as well as the DLR for a given rank. So even a rank 10 is enough to basically perfectly identify this coefficient. And the story is a bit more nuanced when you look at the second parameter, so the beta for 13. You can see that here the covariance only decreases very slowly, whereas essentially the DLR has more trouble figuring out the correct identification. And as I said, there is also this issue of the DLR having a smaller covariance than perhaps it should have given the system. So this is also a real issue. We probably need a higher rank for this parameter for some reason. Okay, and I think now we are reaching the end of the talk. So just to re-summarize, we have basically developed this end-to-end data assimilation compatible framework. We have used it to derive some sensible DLR KBP equations and studied a lot of its theoretical properties. We have used those to derive a DLR-ENKF system and then basically explored integrations of this in parameter identification problems with basically many different interesting directions of practical issues. And for some future work, which I will also be doing at KAUST, we're going to look at ways to also extend this to particle filters. And with this, I am now done.